Hello everyone, hope you're doing good. So myself Kailash Bharatwaj and I'm going to present my topic Superhard thin films on cutting tools. I'm just going to do an analysis of the various processes that are being used today. So initially, what are thin films? Thin films are layers of materials ranging from few nanometers to several micrometers. So in thin films, it has a combination of a metal and a non-metal. The non-metal occupies the vacancies in the metal. So that's how thin films are formed. And then what are superhard thin films? Superhard thin films are thin films, but they have a value greater than 40 gigapascals. And then why do we need them? Because it improves the physical and chemical properties of the substrate. So if the substrate has a long life and better properties, like it can be used for a widespread commercial use. And then what is the purpose of this research? To suggest a suitable coating technique for a widespread commercial use for titanium alloys only. So the different coating techniques. The first coating techniques that were developed were PVD and CVD coatings. PVD, physical vapor deposition. So that is the first thing I'm going to explain now. In PVD coatings, the substrate is coated in vacuum. Like the gases are loaded into the chamber and then they are heated at elevated temperatures. So here reactive gases are used because it forms an oxide with the metal vapors, and then it enhances the substrate. So what are the advantages of this? The advantages, like it has high wear resistance, then they don't react at any environment. But what are the disadvantages of this coating technique? At elevated temperatures, the PVD coatings deteriorates, and then they have a hardness value comparable to that of a non-coated substrate. And then at lower temperatures, when you're using for titanium alloys, it forms brittle oxides, and then the whole purpose of coating a substrate is lost. So the next technique. Next is the chemical vapor deposition coating. In this we use a coating reactor, and then a controlled reaction takes place between the metal and the precursor gases. Why do we need precursor gases is it improves or it enhances the deposition rate. So that's why we need the precursor gases. And then in this technique, the substrate is loaded into the coating reactor at an elevated temperature, say at around 1000 degrees Celsius. So thin films are formed as a result of reaction between the substrate and the gaseous molecules. And then the advantages of this technique is, like, the final product obtained has high hardness, higher wear resistance, and it exhibits excellent coating finishes. And then the disadvantages. While coating titanium alloys, the main problem with CVD coating is that the presence of microparticles hinders the coating rate. So that is the main disadvantage of this technique. So we need a technique where the microparticles can be eliminated so that we get a better finished products. So this technique is not suitable. So moving on to the next technique. So the diamond coatings. The limitations of the PVD and CVD promoted the concept of using diamond coatings. In diamond coatings, the diamond is a very hard substance, as we all know. It has 100 gigapascals of strength, and high thermal conductivity and low friction coefficient. So this technique can be used for a widespread commercial use. So what are the advantages of the cutting tools? Like the tools have longer life, and then it has high grinding efficiency and then low grinding force. And then in this technique, there are no microparticles. The microparticles is completely eliminated. So how the diamond coatings are formed is, first the carbon substrate phase is broken, and then we introduce the substrate, the particles on the substrate, and then the particles are grown. And then diamond coating is how they are used. They are generally used as abrasives, chip breakers. Like the hard surfaces breaks through the metal that is being cut, and that's how you can cut even at higher speed and higher hardness materials. But such a highly used material has many disadvantages. First, the diamond coatings forms oxides when machining a ferrous material. So it cannot be used for ferrous material, and ferrous material contributes about 31% of the materials that is being used worldwide. And that's the first disadvantage. Second, then the carbon and cobalt interactions present in the hmm, in the one that's in the machining material, and it forms it like a good coating technique is, I mean, a good adhesion cannot be achieved. And then moving on to the next coating, um, CBN it has a structural analog to that of diamond, and it has a strength of 60 gigapascals. And then in this technique, like a high level of elemental boron is needed, because the boron forms boron oxides and prevents the surface from further attacks. And the CBN coatings offer combined advantages of high hardness and wear properties, but the limitation is the presence of compressive stresses in the films. So when you are machining a high hardness material, the compressive stresses breaks the coatings, and we won't get a better finished product. And also you can just coat a thickness of 0.3 to 0.5 micrometers. So yeah, more research is required so that we can use it for a more commercial use with higher coating rates. So the last technique that I'm going to discuss today is the filtered arc deposition. It's the most suitable technique for titanium alloys because the presence of microparticles is eliminated. So how it is eliminated is, like, we use a 90-degree magnetic vacuum duct. The magnetic vacuum duct, it removes the plasma particle, the substrate particles, and then it makes sure that you get a better coating. And then, like in this technique, it uses, there are two types of coatings two techniques that can be used for this type of coating. First is direct deposition. Next is the ion assisted beam. In the direct deposition technique, like the titanium material is directly deposited on the substrate. That is the direct deposition. And in the ion assisted, they use a secondary ion source. The secondary ion source, generally they use a reactive or a noble gas, as it improves the properties. So this is the experimental setup, and then this is how the ions get transferred to the substrate. And then the pump, that is the magnetic arc that sucks the microparticles away from the substrate so that we get a fine coating. So the research design, the existing method uses a 90-degree vacuum duct, as I said, but the disadvantage of this technique is that by using the 90-degree magnetic vacuum duct, mechanical properties get altered, and then the energy consumption is much higher because a positive voltage has to be maintained so that the plasma is transported outside the substrate efficiently. So a solution is needed for the existing technique. So the solution that I am suggesting is that you can use a floating bias duct, like which is self-inducing, so you don't need much power, like the power requirement is very low, and then better Young's modulus can be achieved. So this forms an ideal alternate to the existing method. So coming to the limitations of my research, the proposed design is just based on the theory, like it is not experimental. So, and then the second is, the whole research was centered around titanium alloys only. So hope you like my presentation. Thank you.